Good afternoon to all of you. Welcome to this joint ICRP and ICRU session on the innovation in dosimetry. I am Vincent Grégoire, chairman of ICRU, which is, as you may know, the International Commission of Radiation Unit and Measurements, and I have the pleasure to share this session with François Bochu from Lausanne, and I will introduce François just before his lecture. So we have 5 lectures with 20 minutes or 10 minutes. We will have the questions and answers at the end of the session. So it's my privilege to introduce the first speaker, which is Thomas Otto from CERN. Thomas is the Department Safety Officer of the Technology Department of CERN in Geneva, Switzerland. He mainly works on the wide spectrum of topics on occupational health and safety at the accelerator facilities. He has been involved in different expert groups for personal dosimetry and is current commissioner of ICRU. So Thomas, please, we are willing to listen to you, and you have 20 minutes to discuss about operational quantities for external radiation exposure. Please, okay. Thomas.
Thank you very much, Vincent. I give you a report on ICRU report 95, which has the title New Operational Quantities for External Radiation Exposure. And this is a report which has been published jointly with the ICRP. The contents of the talk are that I introduce very briefly protection and operational quantities. I talk about the new operational quantities in ICRU report 95. I explain the changes on the conversion coefficients for whole body dosimetry that this will have, and then go to the consequences for dosimetry in realistic radiation fields and for the response of common dosimeter types. And then I summarize the report. As a disclaimer, this talk will expose you to some of the complexities of radiation protection quantities, as has already been said yesterday, that everything is very complicated, but I hope that I can show you that there is a potential for simplification in the matter of this report. So talking about protection quantities in an ICRP symposium is like carrying owls to Athens, as one says, but I want to be very brief. You know about the effective dose, which is for estimating radiation detriment to the whole body, and the tissue equivalent doses to the eye lens and local skin. These quantities are defined in various reports. For the whole body dose, the phantom is described in ICRP report 110, ICRP report 110, and the conversion coefficients are published in the report 116. This is all very nice and has a lot of foundation and has shown that it's very practical and useful to use. However, these quantities cannot be measured. If you would like to measure effective dose, you would need a dosimeter which has the size of a mannequin in a shopping window, for example, 60 to 70 kilo heavy and fully instrumented. So that's not very practical. Therefore, one has a need for operational quantities which are defined in a single point and which can be used to calibrate dosimeters and monitors. These operational quantities have been defined by the ICRU, the last ones in report ICRU 39 and a few following ones with more details, and they are defined as the absorbed dose D in a given depth times a quality factor, and this leads to a dose equivalent. And the absorbed dose in the depth D for whole body exposure 10 millimeters is done in simple geometric shapes which at the time were thought to be very practical for numerical calculations like spheres, slabs and cylinders. The relation of the quantities is shown in this graph, and here you see this full picture of complexity of radiation quantities. On the top we have the physical field quantities, the fluence, the kerma or the absorbed dose, and on the left side, now only for whole body exposures, the effective dose, which is calculated with anthropomorphic phantoms, On the right side, the operational quantities, the ambient dose equivalent and the personal dose equivalent, which are calculated with simple geometric shape phantoms. And in addition, they have a quality factor Q, which depends on LET, whereas in the effective dose, the quality of radiation is described with the radiation weighting factor, WR. And then you can imagine that although the integrals in the last box look quite similar, that only that the results, the numerical results that you get out from these two very different prescriptions are never really the same, but you have really differences, and the trend with energy is also very different on the two sides. And then the final box on the lower right is about the measurement. That's then yet another response function of the instrument, which wants to prescribe as precisely as possible the operational quantities, and also there are deficits, and this makes the field, of course, immensely complicated. The new operational quantities in the ICRU report 95 are now based on a different paradigm in which we say that the operational quantities are the product of a field quantity in red. Here it's deliberately chosen fluence, but it could also be karma for photon radiation fields, multiplied with a conversion coefficient. And the conversion coefficient is now calculated instead with these geometric phantoms, with the same anthropomorphic phantoms as the protection quantities, and it also uses the same weighting coefficients, WR and WT. And that means that we get a better approximation of effective dose and tissue equivalent dose simply by definition. Other elements of ICRU report 95 are that the tissue effect dose, the quantities to limit the tissue effects, the local dose to skin and to islands, are defined as absorbed doses. And I point to the last talk in this session where the colleague is wants to open a discussion on if this is really totally the best way to only use absorbed dose. And report 95 also contains many more radiation types and a much wider energy spectrum than in previous reports with conversion coefficients for operational quantities, in order to take account of workplaces which nowadays are, for example, at accelerators, and which are not covered by the conversion coefficients to the present operational quantities. No, this was wrong. Well, here. What changes for whole body personal dosimetry? We go away from the slab phantom and the quantity HP10, which is the dose in 10 millimeter depth in the slab phantom multiplied with the quality factor, and go to the personal dose HP, which is calculated as the weighted sum over organ doses in the anthropomorph phantom, exactly like the effective dose. And instead of the so-called expanded radiation field, we have the plane parallel radiation fields from a defined direction, but this is pretty similar. What is going to change? Here I show you the conversion coefficient from karma in air to the protection quantity, effective dose in AP direction for photons. And this is now the conversion coefficient for the quantity HP10, which is our present operational quantity. You see that there's an overestimation over the whole range of energies, which is about 15% in the energy range of radionuclides, but it can be up to a factor of 5 on the left end of the spectrum where very low energies are. And what I don't show here, it's also quite high at high energies, although this is of less importance for photons. And now the blue curve has changed into a green curve, because the green curve is the one for the new operational quantity personal dose. And I have also noted now these these overestimates of the present operational quantity. In the energy range typical for radioisotopes, there is only a small change to be expected, whereas at low X-ray energies, the changes can be quite important. For area and ambient dosimetry, we use at the moment the so-called ambient dose equivalent, which is again the dose in 10 millimeter depth, and this time in the ICRU sphere, times the quality factor in the so-called expanded and aligned field. And this is such a complicated thing that I don't want to spend my time on explaining what the expanded and aligned field is. In the new quantity, we make a maximization by taking the personal doses from all possible angles and directions and take for each energy value the highest. And then we can plot this curve and we will have the so-called ambient dose. I show this at the example of neutrons. This is a family of the different incident directions of neutrons and the conversion between fluence and the quantity effective dose. This is the quantity H star 10 for neutrons, ambient dose equivalent. And you see that there are some underestimations in a range of neutrons which are critical at accelerators in the 10, 20, 50 MeV range. There is a slight overestimation at low neutron energies, but this is not very important because they do not contribute a lot to the dose. And now the new curve is always at the highest curve of this family. So it starts with AP direction, then it goes for a very short energy interval to PA and finally to ISO. And this maximization says that the curve is always at the highest possible conversion coefficient, no matter where the radiation is coming from. That's the maximization in the quantity for area dosimetry. And now we have the same graph as before, but it looks much more cleaned up because on the left branch and on the right branch, you see already that there are the same phantoms and the same weighting coefficients, and the integrals become practically also the same, only that we can take the personal dose under different angles, angle alpha. We can have it under 90 degrees, under 0 degrees, under 75 degrees, but it turns out that the numerical values of effective dose and of the operational quantities in the same radiation field at the same energy will now often be numerically equivalent. That means that we have a better representation of the effective dose with the new quantities. What does it mean for radiation fields? This is a result of a Monte Carlo study about activation at an accelerator workplace, but it could be similar, for example, in a nuclear utility where you have activation issues. You find that the ratio between the new quantity and the old quantity, ambient dose divided by ambient dose equivalent, is about 86% for photons, and that's just because all radionuclides fall into the band of energies where the ratio of these quantities is these 86%, as I had shown before on a view graph. For electrons, it's quite interesting because electrons are weighted higher with the new quantity, and if one would have workplaces where the radiation is predominantly beta, one would have to take more attention. It also says that the quantity H star 10 or HP10 for electrons may be underestimating. At low energy X-ray spectra, which are surrogates for workplaces in radiology, you see on the left a spectrum which is done with a 20 keV tube voltage. In blue is the fluence spectrum. In orange is the spectrum weighted with the present conversion function for ambient dose equivalent or personal dose equivalent, and in green for the new quantity. And the areas under these curves are proportional to the dose value, and you see immediately there is quite a big difference, about a factor of 5. On the right are diagnostic X-ray calibration spectra, which are used to calibrate instruments in medical practice, and they can be used as a surrogate for workplace spectra in medical environments. And you see that the upper curve represents H star 10, the lower H star, and over a wide range of these dots that you see there, you see that the new quantity H star is about 50% from H stars 10 in these broad X-ray spectra. This means that there is an influence on the dose on medical personnel. The measured dose with the new quantities would go down for medical personnel, or others said, we are presently overestimating effective dose with the present quantities and the present dosimeters of medical personnel working in such fields. I come now to the question of measuring these new quantities. In order to measure the quantity, the response function of the dosimeter should follow ideally this curve here, which is the conversion coefficient of photon radiation as a function of fluence. But present dosimeters follow this curve, which has this overestimation at low energies built in. You can see that if you only measure at high energies, then dosimeters can be easily recalibrated. But at low energies, you would have to change the energy-dependent response function of the dosimeter. Here's an example of survey instruments. The survey instruments, on the left, a Geiger-Müller counter, on the right, an ionization chamber, have, and there is, sorry, I mixed up a little bit. The plot for the Geiger-Müller counter is the one on the right, but I mixed up the photos and the plots, sorry for that. You see that the curves are running more or less, I cannot say parallel, but they are very similar to each other. And you can imagine to make a recalibration at cesium 662 keV energy, and then the two curves will fall over each other. This is possible because these instruments have a cutoff energy at about 50 keV, as you can also see on the graphs. So it's not a problem. You can, in future, you would be able to use your present instruments. You have to calibrate them by either in the software, or there's sometimes a little calibration screw on them, and you can continue using them. However, personal dosimeters have to measure very low energies. The IEC has written the reference values for personal dosimeters to be accepted as dosimeters which can be used for legal purposes, and they demand that personal dosimeters measure down to 15 kV or 20 kV radiation. And if we would take a present personal dosimeter with a response curve which is rather good and flat for personal dose equivalent, here in red, then for personal dose, they would of course overestimate the quantity, the contributions to radiation from very low energy photons. This is again not very important if you have workers to monitor who work, for example, in a nuclear power plant or in an accelerator, where radiation comes mainly from activation and typical radionuclides. However, persons working close to a patient who is irradiated with low energy X-rays, and where you are, as a medical practitioner, irradiated by the backscattered photons, would pose a problem for these dosimeters. There is no other way than to redesign either the filter of these dosimeters or the algorithm, or both. Attempts are already being made with presently existing dosimeters. One can find ways around. They are not yet very satisfying, but there will be time to implement these changes. A word for the response of neutron monitors. Already nowadays, with our present quantity ambient dose equivalent, neutron REM counters give a reasonable estimate, which is okay for radiation protection, but you wouldn't claim that this is precision metrology. On the left, you see the response curves of a whole family of REM counters, and the black lines in there are the acceptance limits which have been stipulated by the IEC, and the response curve of a REM counter has to be between these black lines in order to be acceptable for measurements. If you switch to the new quantity, you get to the curve, to the family of curves on the right view graph, and you see that you could apply a little calibration factor to lower this family of curves, and if one then moves around these black lines a little bit, then everything gets into order again. And REM counters will continue to give reasonable estimates of the radiation dose in neutron fields without asking more from them than what they can deliver. People always say now you tie the operational quantities very closely to the effective dose. What happens if the ICRP is going to change effective dose? For example, going to different phantoms. Here's already part of the answer. ICRP is now discussing to change from the voxel phantoms with which the present reference values are calculated to mesh-type phantoms. And on the left, two view graphs, photons and neutrons, you see that the dots and the symbols for the mesh-type phantoms do not deviate in any dramatic way from the lines, which are the reference values calculated with voxel phantoms. There is a difference for electrons. This comes from the fact that the voxel phantoms cannot represent properly the skin, which is the only organ which is impacted by low-energy electrons. However, it turns out that the shape of the curve that you see by these red circles on the rightmost view graph is exactly the one that the ICRU has obtained for the conversion coefficient for the so-called local dose to skin, which is the quantity which is there for protecting against deterministic effects on the skin. So we are not surprised, and whole body dosimetry in very large radiation fields for electrons is certainly not the first worry of a radiation protectionist. So one will have to formulate this correctly, but it's not a worry that in this plot at lower energies below 100 keV, the electron curve are deviating. Conclusion of the talk, the operational quantities are now defined in a consistent manner to the protection quantities using the same phantoms and weighting factors. That makes the system of quantities in radiation protection easier to understand, and we get rid of a whole family of phantoms for the definition. Numerical values and their trends with energy will be coherent with the protection values. The changed dose values in realistic radiation fields do not warrant the changes in RP practice. There are additional studies required for radiation fields in different professions, in particular medical profession. Dosimeter types need to be adapted, in particular personal dosimeters for photon radiation. And so far, these quantities are also safe for the future. They are not affected by the change, by the prospective change to mesh phantoms. Thank you very much for your attention.
Okay, thank you very much, Thomas. I think it was really clear. Hopefully it was also for you. If it's not, keep your question for the end. He will be able to answer any question you have, so that's good. The next presenter will be Ruth Wilkins. Ruth is the chief of the Ionizing Radiation Health Science Division and, in Canada, and she is also a research scientist. She actually oversees the biological research on the health effect of ionizing radiation in the Consumer and Clinical Radiation Protection Bureau at Health Canada. This includes providing guidance to the researchers in the division and supporting the needs of the laboratory research. Ruth, you have the floor.
Thank you for that kind introduction. And thank you to the organizers for inviting me to give a talk about this case study that we came across at Health Canada, where we do biodosimetry for overexposures for radiation. And this was a case, a biodosimetry case that came to us and looked like quite a typical case, but as we went through and studied it, we found that there were some complications that required a little bit more deeper dive into what was going on. So for those of you who are not familiar with biodosimetry, just a little backgrounder, that biodosimetry is a method for measuring how much radiation someone's been exposed to when there is no physical dosimetry available. So it can be used in several different cases, like an accidental exposure. Sometimes we get cases where someone has received a dose on their physical dosimeter, but they don't agree that they've received that dose, or the dosimeter has been compromised. We also use biodosimetry for astronauts, we can look at their blood samples before and after they go into space, or in the case of a radiological terrorist attack or dirty bomb or nuclear power plant, or some large exposure where there might be thousands of people exposed to radiation. We have strategies for dealing with with large populations. But in this case, it's just this very small case where we had a few potentially exposed individuals. So for biodosimetry techniques, traditionally we take whole blood. We look at either the dicentrics, which are a marker of damage, I'll explain. There's also the cytokinesis block micronucleus assay or translocation analysis. These are all methods for measuring damage to the blood induced by radiation. So just to explain a little bit about the damage to the chromosomes, the type of damage can really be classified as being stable or unstable. So for unstable damage, this is damage that is lethal to the cell, so the cell is unable to go through mitosis. It shows up as gross chromosome changes, and it renders the cell unable to pass through mitosis. And these disappear over time because these cells are not able to cycle, or the stem cells are not able to generate new cells. So an example of this is a dicentric, which you can see from the diagram how those are formed. If you have two chromatids that are irradiated, they are both broken. Sometimes the two pieces with centromeres will join together and form a single chromosome that has two centromeres, and then you also get a fragment with no centromere, which is called an acentric fragment. So when this piece goes through replication, it takes this form that you can see. I don't know if I have do I have them? I guess I do on this side. You guys over here can see where I'm pointing. You get this form where you have a chromosome with two centromeres and an acentric fragment. And you can see this is an actual metaphase spread of chromosomes where you can see this type of damage, the dicentric and the acentric fragment. The other type of damage is stable damage, and this is damage that does not stop the cell from dividing, so the cells can continue to grow, divide, and generate more daughter cells with the same type of damage. And a good example of this is translocations, which can start by the same type of damage. You have two chromatids that are both damaged by the radiation, and then they just switch pieces. So it's just a translocation between two chromosomes. And if you looked at those chromosomes with just a solid stain like this, you would not be able to see that type of damage, but we can look at them with whole color paints that you can see the translocations between different chromosomes, and they're quite nice to score, easy to score. So the dicentric chromosome assay is really the gold standard for biological dosimetry, and you count unstable chromosome aberrations in white blood cells from an individual sample and just enumerate the number of dicentrics per cell. It's very sensitive and apparently specific to ionizing radiation, although we might question that by the end of this talk. There's a low background. Typically, you would, in unirradiated individuals, if you count 1,000 cells, you would see 0 to 2 dicentrics in 1,000 cells. And if you score 1,000 cells, you can get a sensitivity of about 0.1 gray for their dose estimates. But this damage, because it's unstable, it decays with time with a half-life of about 3 years. So it's really best suited for acute and recent exposures. Translocation analysis, which we do with fluorescence in situ hybridization, this allows us to count the stable translocations, which are then long-lasting, and they're good for chronic exposures or exposures in the past. They're not as specific to radiation as dicentrics and have a lower detection limit of about the same. This is improved if you can get a pre-exposure sample because the amount of translocations in someone's blood varies quite differently due to other lifestyle factors or age or gender or sex. So we use this for astronauts because it's very easy to get their blood sample before they go into space, and then we can compare when they come back from space about the damage. For both of these, and for most for biodosimetry techniques, one would create a calibration curve by taking someone's blood, irradiating outside the body, generating a curve of the damage as a function of dose. And then when you get a sample that's been exposed, when you don't know the dose, you can just read that, that dose off the calibration curve. So back to this case. So we had originally one case where we have an agreement, Health Canada has an agreement with the Canadian Nuclear Safety Commission that we provide biodosimetry for suspected occupational exposures to ionizing radiation. So in 2014, Health Canada was approached by the CNSC to evaluate a non-nuclear energy worker who was expected to having been exposed to industrial radiography in 2011. So the dates are important here. get the call in 2014, but the potential exposure occurred in 2011. So we went through our usual analysis. We looked at the dicentric assay, and we found 9 dicentrics in 1,004 cells. And if you remember, I said that typically an individual will have 0 to 2 dicentrics in 1,000 cells. So this was significantly above background. So when we saw this, we went and we did the FISH analysis, and we saw 35 translocations detected in 8,000 cells. And we did the dose estimate, taking into account the time since exposure, the age of the individual, and the results from both assays. We pulled all this data together and came up with a response that the dose that this person received was about 0.1 gray with an upper limit of 0.2 gray. So this was considered borderline case detectable by these assays, but we thought we'd done a fairly good job on our dosimetry. We published this data, and that was the end of that case. Until in 2017, we were called again by CNSC, and they had another 7 of these workers from the same industrial company who thought that they had been exposed to the same industrial radiography incident back in 2011. So now we're in 2017, and we're now about 6 years past the exposure. So we drew blood, we did the dicentric assay, we did translocation analysis with FISH. We scored 1,000 cells for dicentrics, and 10,000 cells were scored for the stable translocations. And at this point, we got the Ministère de la Santé et des Services Sociaux were also involved as these were workers from their jurisdiction. So this is a summary of the dose estimates that we determined. So for dicentric analysis, all of the individuals had a frequency between 5 and 9 dicentrics per 1,000 cells. So they were all above background. So this is an indication that there was some sort of DNA damaging agent. It's above what would be expected if you were a chemical exposure in the literature. But this data was not corrected for time since exposure or for previous medical exposures. And for the translocation analysis, we had, you can see from the red bars, we had very large error bars because we're very close to the limit of detection for this assay. And all the 95% confidence intervals included a 0 millisieverts. So we decided to focus on the dicentric analysis. So this was very puzzling to us because if this was a single event that had occurred in 2011, you would expect to get similar results from the 2 assays after correction for the time for the decay of the dicentrics. But here you can see that the levels are fairly similar without any correction for time since exposure. So we were puzzled at this point what was going on. So then we did a correction for, just looking at the dicentric data, we did a correction for previous medical exposures that was made based on medical records. So any exposures that had occurred since 2011 to the time of the analysis. So you can see on the 3rd column in that table, this is the age, what we call the age medical dose. So what the dose would be expected after, time after exposure. So we subtracted that from the dose that we calculated from the dicentric analysis and found the residual dose. And then we corrected that dose for the time since the supposed exposure. And you can see from the graph on the right that the green bars are now representing the corrected dose for both medical exposures and time since exposure. So you can see it looks like these individuals had received a very high dose. And if you look back again to the FISH, the translocation analysis, which is the red bar, there's very little agreement. So the dose looks much higher based on the dicentric than it was on the translocation analysis. So what's going on here? So with the help of our colleagues in Quebec, we started trying to determine what was going on with this sample and what could be some other possible scenarios that would give these types of results. So we thought about, was there exposure to any radioactivity in their workplace, that they were constantly being exposed to radiation, which might indicate that the higher dose that we determined. but there were no thorium welding rods being used, and then it was very unlikely that they were being exposed to radioactive materials because there are lots of things in place to ensure that there's no radioactive material around the workplace. So the other thing that we thought was that all of these workers were welders who get exposed to heavy metals while they're working. And so there has been some evidence of additive effect for radiation and other contaminants. So if you think of like radon and smoking, there's some synergistic effects there where you get additional damage. So there are some possible explanations how a co-exposure to a heavy metal and radiation could increase the damage that you see in the chromosomes. One being that maybe the physical interaction between the metals near the cell's nucleus are increasing the absorption of the radiation at that site, so causing a larger effect from the radiation. Or perhaps just the presence of the metals will interfere with the DNA damage and repair mechanisms, so that could alter the outcome. So there's sufficient evidence in the literature that points towards this additive interaction. It's difficult to quantify the impact on the presence of dicentrics in the blood. So there are a lot of questions that this raised. We don't have all the answers for this. We looked at maybe there were more acentric fragments, but there was no evidence that there was a difference from what would be expected from a radiation exposure, whereas with a chemical exposure, you might expect to have a greater number of acentric fragments. So as I say, this actually raised a lot more questions than I think we answered. So overall thoughts about this case are that, first of all, the dicentric analysis gave a higher dose than the translocation analysis with fish. Even when we consider the recent medical dose, there were welders with little or no medical exposure that still had a significant number of dicentrics. If the damage was solely due to radiation events, more than 6 years previously, the dicentric analysis should have given a lower dose than the fish analysis due to the decay of the dicentrics with time, but this was not the case. The frequency of the dicentrics is above what's described in literature for various chemical exposures. The welders were also exposed to heavy metals, so cadmium, manganese, chromium, nickel, and arsenic in the water. And based on the witness of response, the welders were likely to have been exposed to radiation. But this is just by witness reports and by reconstruction of what a possible scenario was. So the high level of chromosome damage detected could be due to a combination of short-term radiation exposures with a chronic chemical exposure. So to conclude, the biodosimetry results indicated the possibility of workers being exposed to radiation during the mishandling of radiographic equipment. The damage was higher than typical background, but due to the time since the exposure and the radiological procedures, the uncertainties in the dose estimates were quite high. So there were some recommendations that came out of this investigation. One was to improve the physical dose reconstruction, to improve improve the estimates of the dose from the radiological procedures, the medical ones that were done after this potential exposure. Also to perform biodosimetry on the radiographer who was the one implicated in the incidents with the radiography and who should have been wearing a badge. And then the other one, which we were unable to get the resources to support, but I thought would be a very good control, would be to perform biodosimetry on some matched workers who are really not exposed to radiation, to see maybe maybe the increased DNA damage is due just from their chronic exposures to heavy metals and there was no radiation event. There's a very strong suspicion that the workers were occupationally exposed to heavy metals, and toxicology examinations should also be performed on these workers to see if we could detect any of these heavy metals in their biological material. So this was a very unusual and complicated case. It really demonstrates the complexity of biodosimetry and the implication of confounding effects that you need to take into account more than just the radiation when you're doing this type of analysis. So I'd just like to acknowledge the people who contributed to this. There are a few at Health Canada. Carolyn Purvis was involved with this from CNSC. Tristan Barr, who was CNSC at the time but is now actually working for Health Canada. And then the Ministère de la Santé et des Services Sociaux du Québec, they were very much involved in doing some of the deeper dive on the analysis with considering all the other confounding factors. Thank you.
Thank you very much, Ruth. Our next speaker is Chan Kim from Korea. Chan is a professor in the Department of Nuclear Engineering at Anyang University in South Korea. He develops innovative technologies in radiation engineering and medical physics. For instance, he developed a way to localize radioactive or nuclear material in the field or a new imaging technology. Today, he will talk about mesh-based computational human phantoms that are presently developed for ICRP, and actually he is a member of Committee 2 of ICRP, in which this kind of development is heavily appreciated. Chan, you have the floor.
Thank you, Chairman. The title of my presentation today is Adult and Pediatric Mesh-type ICRP reference computational phantoms, which were developed in our task group. There's task 103. And this slide shows the current ICRP reference phantoms we call VRCPs, that's voxel-type reference computational phantoms. And there are 2 adult phantoms and 10 pediatric phantoms. These phantoms are much better than the previous phantom, previous stylized or mathematical phantoms, but still have some limitations. That is that we can see some stair-stepped surfaces, which is not fully closed, and also thin or tiny structures cannot be represented. For example, the stem cell layers in the alimentary tract organs or respiratory tract organs cannot be defined. So it was necessary for ICRP to use 12 additional stylized phantoms for those coefficient calculations. There are some more limitations, but the most important thing is that the phantoms were matched to the reference organ meshes exclusive of blood content. So the organs are smaller than usual by 3 to about 20%. And because of that, the neighboring organs are not in contact, which could cause problems in internal dosimetry for low energy photons and electrons. So these limitations were discussed in ICRP Committee 2 meeting in Abu Dhabi in 2013, and the committee decided to convert the voxel-type reference phantoms into a high-quality mesh format to address these problems. And it was general understanding and consensus that the new phantoms, which the task group will develop, will replace the current voxel-type reference phantoms following the next set of general recommendations. To the project, we established a task group. There's task 103 in 2016. And this slide shows the membership of task. And you can see we have Maria Jankel, Nina Patushihan, who developed the adult voxel phantoms. There's reference phantoms, and also we have Wesley Bolch and Chulxing Li, who developed voxel-type pediatric phantoms. These are reference phantoms. Also, we have Keith Ackerman, who developed mathematical phantoms in old days. So we all work together. So we have been working on the project for several years, and we developed a set of mesh-type reference computational phantoms, which we call MRCPs. And these are the developed MRCPs. That is, again, mesh-type reference computational phantoms. We have 2 adult phantoms and 10 pediatric phantoms. And these phantoms are made of mesh, and it's called a tetrahedral mesh. And these phantoms, the organs of these phantoms are closed with surfaces which doesn't have any hole, and also the phantoms, in these phantoms, the organs were matched to the reference organ matches, inclusive blood content. So the organ size will increase a little bit. So now the neighboring organs are in full contact, which is normal. And this slide shows some example of skin models. And as you can see here, the target region, the thickness is 50 micron. The target region of skin is well defined. And this slide shows the alimentary tract organs. And again, you can see there are several layers. And one layer is to define the target region, and the other layers are used for defining source regions. It's long airways. This is one of the most complicated model we have. And if you enlarge the airways, eventually you can see there are many layers, several layers. And there, the red color shows the target region. There's only 8 micron. And the other regions, we also need the other regions to define source regions. This slide shows example of islands, eye models, and teeth model. This is to support the ESRO EPR dosimetry. Blood in large arteries and veins, muscle model, and lymphatic node and skeletal system models. So again, this slide shows the developed MRCPs. Then we investigate the impact dosimetric impact of the new phantoms, and this slide shows the effective dose coefficient calculated by the MRCPs, which we developed, and VICPs, which are voxel type reference phantoms, for photons in AP geometry. And here the markers are the values of MRCPs, and the solid line are values of VICPs. And as you can see here, there are not much difference between the values of MRCPs and VICPs, except for very low energy photons. For example, if the energy is 10 keV, which is very low, the difference is about 20 to 30%. So the difference are not large; they are very small. But the situation is totally different if it is electrons, and this slide shows the effective dose coefficient calculated by MRCPs and VICPs for electrons in AP geometry. And as you can see, there are very large difference between the values of MRCPs and VICPs. We see about 20,000 times of difference for low energy electrons, and this result is true for electrons and for any other charged particles. This is about the validation of MRCPs, which is also very important. For validation, the MRCPs were first visually inspected in 3D by the task group members and the lead anatomist, who is also our task group member, step by step during development. And after the development, the MRCPs were again visually inspected by a group of anatomists independently. And the organ depth distributions and chord length distributions were calculated and compared with those of VICPs, which are current voxel type reference phantoms. And those coefficients were also calculated and compared with those of VICPs extensively. For example, for adult phantoms, we compared about 2,000 cases for external exposure and 2,400 cases for internal exposure. And those coefficients were calculated by 3 different codes and compared. So we used the GENT4, MCMP, and Fitch code and calculated values and compared. And finally, the TG report was reviewed by the critical reviewers in Committee 2 and also in Main Commission and go through the publication public consultation, like other report. And there's one more thing. In our case, in our task group, if we develop the phantoms, we first distribute the phantoms to some experts in the world. And so they can use the phantoms for about 1 year and about, again, 1 or 2 years. And then we publish the publication. So we have enough time in advance so people can use the phantoms and check the phantoms and compare the values with the other values. So that is our way for validation. Even though we developed the computational phantoms for ICRP, those coefficient calculations, so we also developed phantoms with different bite size and postures for some other applications. And this slide shows the percentile specific phantoms, 9 male phantoms and 9 female phantoms with different height and different weight. And these phantoms were included in ICRP publication 145. And we also produced the phantom library. This is an example of adult phantoms. Here, 108 male phantoms, and we have 104 female phantoms. And also, we developed the same library, library of the same phantoms, but with raised arms for some medical applications, or without the arms in this case. So we just removed the arms. This is too small, but the slide shows the phantom library for pediatric phantoms, which were developed from pediatric MRCPs. All the phantoms in the library were developed from ICRP mesh-type reference computation phantoms. Also, we developed phantoms in different postures, like in walking postures, sitting, bending, kneeling, and squatting postures. Also, a research team in Korea developed physical phantoms using the data of mesh-type reference computation phantoms, and also using mostly 3D printing technology. And these phantoms are indeed these days used in Korea for emergency dosimetry. In our test group, now we already developed adult and pediatric MRCPs, and now we are developing pregnant female MRCPs. That will be our last task, and these are almost completed. And this will be complete by the end of this year, so within 2 months, with very detailed fetal phantoms. Thank you for your attention. Thank you.
Thank you very much, Dr. Kim. It's now my pleasure to introduce the co-chair of this session, François Boschou. I'm not sure he needs a lot of introduction. You are all familiar to François. He's a medical physicist. He specialized in ionizing radiation metrology, and then he decided lately to take over the direction of the Institute of Radiation Physics at the CHUV in Lausanne. He's an expert in dosimetry. He's now a member of ICRU, so he's the main commissioner of ICRU. He's also a member of ICRP Committee 2, and we asked François to discuss about what is a fancy topic in the field of radiation oncology. I'm sorry, I use the word fancy because maybe I'm not using it, which is ultra-high dose rate, the so-called flash dosimetry in radiation therapy. François, tell us everything about flash.
Thank you, Vincent. I'm not sure I'll be able to tell you everything about flash. I will concentrate on measurement and metrology more precisely. So anyway, I have to go toward Vincent and explain a little bit what we mean by flash radiation therapy. I don't know if you're familiar with this kind of graph. On the x-axis, you have the dose that is given to the patient. On the y-axis, for these two curves, you have the TCP, tumor control probability. So that's the probability to actually destroy the tumor, if you want. And for conventional radiation therapy and the so-called flash radiation therapy, these two curves are the same. So, okay, so far, nothing really interesting. Well, another curve is important, is the NTCP curve, which is normal tissue complication probability. So that's the probability to have a problem when we are doing the radiation therapy, to induce something bad to a tissue that doesn't want to be destroyed, typically. And this is the curve you have with conventional radiation therapy, and with flash radiation therapy, you actually displace this curve to the right. So you can immediately see the advantage of having this kind of treatment. Well, that means that in very short summary, we can say that irradiation at ultra-high dose rate, because I didn't say that, because flash radiation therapy is directly linked with a very high dose rate in a very short time. So irradiation at ultra-high dose rate increases the differential response, so the separation of these two curves between normal and tumor tissues. Okay, so what is the history of flash radiation therapy or ultra-high dose rate radiation therapy? So this was more or less observed in the 1970s and then forgot. So nobody thought there was any interest in this, even though by retrospect we saw some interesting aspects. And the institute in which I'm working has been interested in this kind of treatment since 2014. So at first by doing preclinical studies. In 2018, we transferred to another animal model, so to the pig. And then we started the first phase 1 trial on cats. Then we had the first human, just one person, human that was treated with this technology, and afterward a phase 3 trial was started. And since the beginning of this year, we have 3 such different machines in our institute, and we are trying to build another one. So it's a big project, well, which worries a little bit me. Okay, that's not what I'm supposed to talk about here. So what is this? How does a beam of ultra-high dose rate look like? Well, as any LINAC output, it's a pulse. It's a pulse beam. So the width of the pulse is around 1 microsecond. The repetition frequency is about 10 to 20 hertz. And what is interesting and what makes the specificity of this kind of treatment is that in one pulse, you can actually adjust the dose between 1 milligray to 10 gray. So you can imagine 10 gray is a huge quantity. That's actually something we don't want to get if we do not deserve it. So that means the dose rate within the pulse can be up to 5 million gray per second. But what is really important maybe is to know the mean dose rate, because we use usually several pulses when we irradiate a patient, and this is between 10 milligray per second to 1 kilogray per second. Mm-hmm. So you already guessed, the treatment is much faster in a flash radiation therapy. It takes less than 0.2 seconds, whereas in conventional mode, it's a couple of minutes. And it has to be repeated in different sessions, so it makes a big difference. Okay, so I want to concentrate on metrology of ultra-high dose rate radiation therapy, and I have to say it's really in its infancy. When I look at conventional radiation therapy, we know that the measurement we do is traceable to the international standards with what we call an unbroken chain of comparison. Well, you know, you have an instrument on site, and you can have a direct link to the mother of all instruments, which lies at BIPM. We have somebody who used to work at BIPM in this room, so if you have any question, you can go to her. So that means we have the international prototype. For absorbed dose, it's typically a calorimeter with a very low uncertainty. And at the hospital level, we have ionization chamber, which have obviously a slightly higher uncertainty, but not that bad, to around 2%, that's typical. The problem we have with ultra-high dose rate is that we don't have anything like this. So we have to do our best to measure the dose. So in summary, that's what we have. Flash radiation therapy does not have any direct link to the BIPM, Bureau International des Poids et Mesures. So therefore, we have to find something else to be able to measure the dose. So for that, the method we used was to use several dosimetric devices that have a link with the international standards. And then we do relative dosimetry with these different systems, and hoping for the best, that the dose we are measuring with this system will be slightly more or less coherent, and therefore we could say what is the absorbed dose in gray with this kind of instrument. So first of all, we chose four types of measurement. Alanine measurement, we heard a lot about alanine before lunch. Film, you never thought we would talk about film again, but in radiation therapy, we are still using quite a lot of films, TLDs, obviously, and also ionization chambers. And any kind of good ideas that we can have. We are currently trying plastic scintillator, diamond dosimeters, well, any kind of dosimetric principle would be useful. The three first ones are more or less dose rate independent, hopefully. And if they are not totally dose rate independent, we hope that different means of measurement will have different behaviors according to the dose rate. They will not all differ in the same way. For the ionization chamber, we had to correct quite a lot. The present ionization chambers are not really usable for flash dosimetry. So in conventional mode, that's the result you have here. In conventional mode, we have a good agreement between those four measurements. Within 2%, that's what we got. And for ultra-high dose rate, you can see it's not as good, but we were really happy to see that there was some relatively good coherence. So that means that we don't have a direct traceability to the international standards, but we have some kind of trust, I think, because we observe quite a good coherence between these different instruments. So now, if we want to go to clinical transfer, because that's the way it is. If I tell you how the medical doctor in charge of this project in my institute is, he would have liked to treat patients 10 years ago already. That's normal. That's the role of the doctors. You can ask Vincent if he has a new toy and he can help the patient, he wants to use it right now. And we are the physicists holding the brakes and trying to make sure that we know what we are giving to the patients. But here I have a series of question to ask. Well, there are some commercial instruments now, but they clearly need to have better diagnostic and monitoring tools in order to control the beam. The ionization chamber, they are not really up to the task right now. The solution that we found was to use current transformer. So it's, well, you can see it's a coil that is just out at the exit of the beam, and we measure the variation of the electromagnetic field, and therefore we can have an idea of what went across. But we have to be quite fast. We have to be quite fast, because if we want to make sure we do not give 10 or 20 or 30 gray too much to the patient, we have to be able to control very fast, because we have just a few milliseconds to stop the irradiation. Especially, I remind you, a pulse can be up to 10 gray. So if you just give one or two pulses too much or too less, too few, it can be a big problem. So we need to have fast and diagnostic and beam control in order to really go to the clinic. And on the safety side, well, the prescribed dose will not be much higher than what we have right now in a few number of sessions in radiation therapy. The issue is really measurement, as you guessed. Here, for instance, you have a Monte Carlo simulation that has been done for the next bunker we are going to build next year. What you can see here is that there is always something that could be measured outside. We deal with ionizing radiation. They are not all stopped in the shielding of the building. So there is something that can go out of the building, and we need to be able to measure that. But right now we do not have instruments that are really traceable and can tell you what is the dose that were presented by Thomas just before. HP10, H*10 right now, well, whatever the definition, we don't have any instrument that is able to measure it on time. We can use passive dosimeters, that's how we did it until now, but we need to have a high signal. We need to have a high signal to measure this. And in practice, we had to deliver several million grays within the bunker in order to measure something outside. And it's a bit ironic because at the end, the radiation protection measurement and the physics measurement are the ones that give by far the highest dose around the bunker. So we want to do the radiation protection as good as possible, but we are delivering much higher dose than we would without doing that. But we definitely need to do this kind of measurement. Okay, for the treatment plannings, TPS can compute the absorbed dose to water, that's clear, but they cannot predict the flash effect, because I didn't tell you, but we don't know how it works. We don't know the biological effect which is behind the flash effect. We have several hypotheses. There are different groups around the world who tries to explain that, but we don't know what's really happening at the cell level. And finally, for the commissioning, well, we have a need to have a chain of traceability. We need to have tools that can be really used and possibly as close as possible to what is done conventionally. So in conclusion, UHDR dosimetry is a work in progress. It is ready for clinical tests, that's sure, but we still need to work quite a lot. There is, I'm sure you will take this home message, there is a lack of traceability, not only for the patient, but also for the public, because for the radiation protection measurement, they are done for the public. And I don't know yet if the regulators will be satisfied with this. Right now they were, because it was a research project, but in the future we'll see. And more fundamentally, we don't know exactly what is the parameter that can explain the presence or the absence of the flash effect. We don't know what is the real process that is behind that. And maybe at the end we will need another dosimetric parameter, because it may not be just sufficient to know during what time which absorbed dose is given. Maybe that will be another parameter that will be useful. So this is still a work in progress, and I thank you for, no, I don't thank you right now. I just wanted to acknowledge my colleagues, because there were a lot of colleagues implied in this, definitely. Okay, thank you for your attention.
Thank you very much, François, for this highlighting presentation. It's my pleasure to introduce the last speaker. Yes, Salah Jeffa from Canada. He's a radiation protection specialist at the Canadian Nuclear Safety Commission, and he will discuss about operational quantity for high-length neutron dosimetry in light of the ICRU 95 report. Please, sir, 10 minutes, please.
Thank you, Vincent. Good afternoon, everyone. So my name is Salah Jeffa, as mentioned by Vincent, and I am a radiation protection specialist with the Canadian Nuclear Safety Commission. So it's my pleasure to provide a brief overview of the work on the operational quantity for high-length neutron dosimetry on behalf of my coworkers listed in this slide. Details on this work are included in a paper published recently in the Journal of Radiological Protection, Volume 42. This work is part of a research project on high-length dosimetry initiated by the Radiation Protection Division of the CNSC. It is funded by the Canadian Federal Nuclear Science and Technology Work Plan and conducted in collaboration with scientists from Canadian Nuclear Laboratories, CNL, and DTEC Canada. This FNST work plan is also under the Atomic Energy Canada Limited as the Program Administration and Oversight Organization. I just wanted to mention there is an e-poster describing the whole project, which started in 2020, and it's still ongoing, and describing the different aspects of the covered by this project. It's also included at this symposium. It's the poster, I think, 072. Back to this presentation. The scope of this work was to review the data in the literature related to compliance with the current high-length dose limit, to address the recent proposed redefinition of the operational quantities for external radiation exposure, and to validate the modeling techniques used to quantify new radiation-weighted absorbed coefficient for the high-lengths presented in this study. Obviously, the contribution of neutron to I-lens dose will be important, where it contributes a significant fraction of the total dose to the length of the eye. As of today, neutron protection conversion coefficient are provided in terms of absorbed dose per unit fluence, picogray centimeter square, as per the ICRP 116, while the current I-lens dose limit is recommended in unit of millisievert, as per ICRP 118. The availability of conversion coefficient for the operational quantity HP3/5 in person-sieverts in picosievert centimeter square for neutron is required, as personal monitoring is currently performed in terms of this quantity. The current equivalent dose limit for the length of the eye is addressed from a neutron perspective, considering the recent proposed redefinition of the operational quantities for external radiation exposure in ICRO report 95, as mentioned by Dr. Otto earlier. The use of radiation-weighted absorbed dose, RBE times D/phi, is proposed for the tissue reaction in the lens for neutron radiation as per ICRP 180, and in line with the recent ICRP revision, paper on revision of the system of radiological protection to keeping the ICRP recommendation fit for purpose. Based on the available data in the literature, we proceeded as follows. MCNP simulations were performed to obtain the absorbed dose and the personal dose equivalent coefficient at 3 millimeter depth in a cylindrical and slab phantoms. Additionally, the absorbed dose delivered to the lens of the eye per incident neutral fluence was computed in a three-dimensional model that incorporated two sterilized eyes into an adult Oak Ridge National Laboratory mathematical phantom provided by the PIMAL software. Details on the realistic eye model are shown in this section in the right side of the slide, while the complete mathematical phantom standing poster is shown in the left side of the slide. In the case of sterilized eye model, application of RBE weighted absorbed dose coefficient is also proposed to provide an RBE weighted absorbed dose quantity. The results obtained from all the stimulations were computed in the anterior-posterior radiation geometry, were compared with related published data from Menger et al. in 2012, from Gualdrini et al. In 2013, and recently by Hertel et al. In 2021, and were found in a very good agreement. This allowed us to validate the modeling techniques used to quantify new radiation-weighted absorbed dose conversion coefficient for the lens of the eye presented in this work. Our data from this work on fluence to absorbed dose conversion coefficient for neutron calculated in the cylinder and slab phantoms are compared with data for the whole lens and radiosensitive eye lens region in a realistic phantom. Ratios of data are also shown in the upper part of the figure. Neutron dose conversion coefficient in the radiosensitive lens of the eye and in the whole lens volume of the eye are quasi-identical in the entire energy range investigated. Dose conversion coefficient in the real eye lens model are in good agreement with those obtained in the cylindrical phantom, while the slab phantom values slightly exceeded those obtained from the real eye lens model for neutron energy above 10 to minus 7 MeV. These trends are believed are primarily due to the unique geometry of the respective phantoms. By ICRP convention, those resulting in tissue reactions, deterministic effects should be coded in gray rather than sievert, which is reserved for stochastic effects. The RB weighted absorbed dose is calculated using same equation used to compute HP3, with the exception that QE is substituted by energy-dependent RBE values for neutrons. The choice was made to use lower RBEs rather than Q's, quality factor, as per table A1 of the ICRP 180 report. However, it remained the problem of the unavailability of RBE data for neutrons below 1 MeV, as you can see in the figure. However, it was noted that the available RBE-N values in ICRP are generally 1/3 of the radiation weighting factor WR for stochastic effects. Also, it was observed that RBE values for tissue reaction induced by alpha particles and fission neutrons appear to be 2 to 3 times lower than the WR values for the stochastic effect, as per ICRP 58 and ICRP 147. Clearly, the definition of the most appropriate RBE-N for tissue due to high LET radiation warrants further research. The aim of this work is simply to propose an approach for determination of an RBE times D quantity for the length of the eye, which better represents the radiological risk for this organ. RBE weighted absorbed dose conversion coefficient, RBE times D over phi in picogray centimeter square, were computed similarly to HP3 over phi, with Q and E being replaced by energy-dependent RBE values for neutrons. This figure clearly shows that HP length 3 over phi calculated in the phantoms are very conservative compared to RBE times D over phi in picogray centimeter square calculated in the realistic eye model, either sensitive or whole length. From the ratios, one can see an overestimation of the dose by a factor of 2 to 5, depending on the energy, neutron energy. This is a consequence of the large Q&E values used in the calculation of HP3 in the cylinder and the slab phantom compared to RBE values adopted in this study and applied to the case of the realistic eye model. I will finish by saying that the work is still in progress and being completed with the aim to provide a full set of neutron fluence conversion coefficient computed for different neutron energy and different angles of incidence from 0 to 180 degree and rotational in a realistic human eye model. The RBE absorbed dose, RBE times D over phi conversion coefficient for neutron exposure are included in these computations, which will be readily updated upon availability of additional or new RBE values for tissue reaction. The proposed approach would provide an operational quantity consistent with the units of the new eye lens dose limits without being overly conservative. Thank you.
Thank you very much, Dr. Jeffa. We have now time for questions. We have 12 minutes for questions before the coffee break. So please. Please.
Yes, hello, my name is Katrin Koch. I'm from a nuclear power plant in Sweden.
Closer to the mic.
Closer, okay, closer. I was listening to the blood dosimeters that you were talking about, the chromosome as a marker for the dosimeters, and there was a big error bar on all the results. So that combined with them actually triggering for chemicals or for metals, is that actually, isn't it a vulnerable system? And I have another question about the 50 keV for the response of the ICRU reports. Is that the 50 keV, is that you said you were going to filter it. Is it a cutoff or is it another kind of filter? Okay, thank you.
Okay, I don't think I caught the point of your question.
Aha.
The error bars are very large, and then you
Yes.
said something about the chemical.
Yeah, so I was just wondering, since it seems a bit of a vulnerable system, since the error bars are that big, can you actually use them as dosimeters?
So the really large error bars were on the translocation analysis because we were working very close to the limit of detection for that assay. But for the dicentric chromosomes, we were getting the amounts that we were measuring were significantly above background. So we can use that data, but the translocation analysis is not very useful for that low dose.
So, what? This works? Yes. Okay, fine. So the new quantities, ambient dose and personal dose, are very similar, proportional to ambient dose equivalent and personal dose equivalent from an energy in photons from about 50 to 100 keV on. So they are just 86% of the ambient dose is 86% of ambient dose equivalent if you have a photon energy, say, higher than about 75 keV. For energies lower, the two curves are not parallel anymore and everything becomes a bit more complicated. Survey instruments are usually massive things because they can drop on the floor or they are made from thick metal for ionization chambers, and therefore they naturally do not measure photons lower than about 50 keV. Photons lower than 50 keV energy simply do not penetrate into the sensitive elements of these instruments. And that's why they are not affected by the more complicated ratio between the new and the old quantities at lower energies. And you can simply recalibrate by applying the 0.86 coefficient. That's what I meant with the cutoff energy.
Other questions in the audience? Maybe I have one for François. All what you told us about flash was for electrons, isn't it? So with photons, do you expect some more difficulties or concerns?
Well, electrons are usually more annoying than photons when we measure them, so that would be easier. The main difficulty with photons will be to produce such a beam, actually, because you know that usually we produce the X-ray beams in radiation therapy by doing Bremsstrahlung from an electron beam. So we managed to have a very high dose rate beam of electrons, but then if we have to convert into photon, we lose typically 90% of the intensity. So there are some projects that hope to be able to have very high dose rate photons, but from year to year they always present the same slides. So I'm wondering if they have troubles to get it.
Sir?
Yeah, thank you. So Simon Boothler from the UK Health Security Agency and ICRP Main Commission. Another question for Ruth, really. I mean, obviously very curious cases, but I think what you're proposing in the end, that there's a confounding chemical exposure which is able to induce dicentrics but not induce translocations. And I find it very hard to imagine anything that can do that, or not do that, as the case may be. Would you care to speculate a bit further?
Yes, I agree with you. But we're puzzled, so we're looking, something's going on there. And we would look at the translocations, we would look at the dicentrics in a match control if we could. But yes, I agree, it's very puzzling.
Sir?
Okay, thank you. Haruki Ogino from NRA Japan. My question goes to Mr. Otto from ICRU. In your last slide, you mentioned about the timing of using the new concept of operational quantity, and you mentioned about the use of mesh time phantom. So could you please explain it again, what you meant in the last sentence in your last slide? Thank you.
Yes. The effective doses at the moment calculated with voxel phantoms, and we have tied the operational quantities to these phantoms. So instead of having for the operational quantities these simple shapes like the ICRU sphere or the SLAP phantom, we use the ICRP reference phantom. Mm-hmm. If now ICRP changes for its reference to voxel phantoms, then we wanted to see if our operational quantities are still conservative. And from the plot on one of the last slides, you saw that the dots are falling on the same lines, which means the voxel phantoms will not make the new operational quantities as published invalid.
Okay, thank you very much.
There was a question on my left,
yes.
Please.
Thank you. Good afternoon, Aurélie Zambert from France. I'm also ICRP member of the Committee 3. I have a question for François regarding flash therapy. Thank you very much for your excellent talk, because you raised all the issues that we have on a metrological point of view, so that was very interesting. And I must admit, I also share your worries regarding these topics on flash therapy. I'm a difficult physicist as a background, so maybe that's why. And I would like to know, as member, you and me, of ICRP, what should ICRP or could ICRP do regarding flash therapy right now?
Well, that's a good question. That was already also asked within ICRU, actually. It's a hot topic. And the answer that I gave, at least within ICRU, was that the subject is really evolving fast. And it's maybe too early to ask ICRU and probably also ICRP to bring advice right now, because well, we are not always really fast to write our report. And we want them to last more than 6 months. So.
Thank you very much.
Hi, this is also regarding Ruth's presentation. I'm Prakash Hande from National University of Singapore and also with C1 of ICRP. I try to, this is just a comment, not a question. I try to avoid using dicentric assay as gold standard in most of our papers on biodosimetry. I think we have discussed this earlier. And the second point is, in our studies, we do see production of dicentrics following arsenic exposure in human blood and also human cells. Of course, they are lesser compared to ionizing radiation exposure. That's the comment.
Sorry, I couldn't get the last bit. There's a horrible echo in here. Just a comment, no question?
It was a comment.
It's just a comment, yeah.
Just a comment.
Yeah.
Okay, thank you. Yes, I need to stop using the term gold standard for dicentric. I've been doing it for years, and I know there's a lot of discussion about that. But it's certainly the method that's been around the longest and one of the most established ones.
If there is no further questions.
There are a lot of questions for you, Ruth, but I have a question, a very simple question. I'm sure you told it, but I probably missed. Why didn't this person have a dosimeter?
So the ones that we were studying were not radiation workers. So they were just in the location where the radiography was happening. And I think the radiographer left the source unattended. So they weren't expected to be exposed to radiation.
Okay.
Any other questions in the audience? We still have 2 minutes to go before the coffee break. If there is no question, I would like first to thank the speakers for their outstanding presentation and the audience for attending the sessions and for the nice questions. I wish you a nice coffee break and come back at 4 p.m., please.
Thank you.